forums. I work for Kaggle, one of the program managers on the team here. Appreciate all your support and fun excitement as we enter the competition. And again, congratulations on a great finish. As you see, we are recording this. This is just to make sure the Foursquare team, if they would like to take a look at it later on, and go back and rewatch it.
Yeah.
Just be aware of that. Generally, the way that this goes is we will. I'll hand it over to Ariel and Zesis to kind of kick off introductions for the Foursquare team.
Sure.
Then they will hand it over to you to present for your team, introduce yourselves. You'll have you go through your presentation and then have some Q&A at the end. The Foursquare team may jump in and ask some questions as you see fit, or as they have them as they come along. We have a full hour blocked off, but usually doesn't need the full hour. Just want to make sure you're aware of that. So no need to feel like we have to continue to add things.
Yeah.
And I think that's pretty much it. We are completing a few of these calls over the next, I think the rest of this week, I think a little bit, maybe early next week. In doing so, once those are all complete, we will then hand off your prize money.
Oh, that's great.
Here.
Yeah.
Before I hand it over to Zesis and the rest of the Foursquare team, what questions do you have? Anything that I can help answer before we dive in?
So far, not. I think it should be from Foursquare.
Okay, great. So then I'm going to hand it over to Ariel and Zesis. I'm going to put myself on mute and kind of fade into the background, but I'll be here the whole time. We'll look forward to hear what you have to show us.
Sure. Yeah.
Ariel, are you on the call?
Hi, yep. Hi, this is Ariel from the Foursquare side. I lead our B2B marketing team and worked closely with Zesis on our team to organize this competition. So we really appreciate all the amazing work that you did, and we're excited to learn more, and would love to, continue the conversation with you to, spotlight the great work that you did in our marketing efforts after the fact. So I have Nadine here on my team as well, and I'll hand it over to Zesis to introduce himself as well.
Thank you. Yeah, let's have a quick round of introductions so that you know who you're talking to from our side, and then we'll get some time to listen to your solutions. So I'm Zesis. I work for Foursquare for the last around five years as a data science, and most recently as engineer manager of a data science team that works on places. So problems related to data matching, entity resolution, similar to the one that we had in this competition. So congrats again from me, and excited to hear your solution. Anastasia, do you want to introduce yourself?
Sure. I am Anastasia. I'm an engineer on the Places team. I've been with Foursquare for 3 years now, and have worked on this type of problem in lots of different settings. So excited to hear about your solution.
Are you in charge of such kind of the matching area in the Foursquare?
I don't think anyone is in charge of it.
Yeah, I know this is not the realistic data. Yeah, I just curious.
But yeah, Zesis I think has more expertise than I do, but we've both worked up these types of problems.
Got it. Yeah, thank you.
Shall I pass it on?
Yeah.
Okay. How about Chris?
Sure. I'm Chris. I've worked at Foursquare 5 to 6 years. Closing on to 6 right now. I'm mainly an engineer, software engineer, but I have experience working on similar problems to this, or like not working on, but like maintaining the system that does something similar to this. So that's where I'm coming in. And I work under Zesis, and that's about it. I suck with these intros, but yeah, that's I won't bore you anymore. I'll pass it to Saurabh.
Hi, I'm Saurav. I'm a data scientist on the Places team. I'm fairly new to Foursquare, so I've been here for 3 months, not years. But I'm very excited to meet all of you and looking forward to learn more about your solution.
Okay. Yeah, so in this case should be from our side, right? But I have one slide for there is everyone's short bio is there, so I think I can share the screen. Should be this whole slideshow. Oh, can you see my screen?
Yes.
Yeah, I can see it.
Oh,
Thanks.
great. Yeah. So yeah, I think I will go through from the beginning later, but maybe we should just do self-introduction from our side. So I'm Takami Sato. So I think the different name appeared in the meet because I didn't know how to change name. But my name is Takami Sato. I'm currently the computer science PhD student at UC Irvine. But I was software machine learning engineer in Japan for 5 years. And actually, these Yuki and Tom are the ex-colleagues. So that's why we team up at the beginning of this competition. Then later, we team up with 2 guys in the first rank. So in the research, I'm doing the autonomous driving, security of autonomous driving. Sounds very fancy, but it's an urgent topic. So yeah, if I have a time, I can present my research as well, but not that time. Yeah. So yeah, I will pass to the, okay, let's go this order. So Yuki, could you say something?
Okay, hello, I'm Yuki Abe. I'm a data scientist at DNA Incorporated for 2 years. I'm mainly developing image generation AI model. And sometimes I participate in Kaggle competition for that's it.
Yeah, sounds like other job, right? So I think the DNA is very kind of like a positive for participate. So for the employees' participation in the Kaggle competition because it's kind of like a good educational kind of like a process. So that's why we can also use the competition as a resource in the DNA. So I think such kind of things Yuki was about to say.
Yeah.
Okay. Next to the Tom.
Okay, thanks.
Tom.
Hi. Okay.
Yeah,
hi,
I can hear you.
Kaggle name is same Tom. Same as Yuki, I work at DNA as a ML engineer. And I mainly do basketball team analysis and AI solution. Nice to meet you.
Yeah, sounds good. So Kohei, next.
Hi, I'm Kohei Yamasa. I'm a master student at the Kyushu University, and I study plant phenotyping. So okay. Nice to meet you.
Oh yeah. I'm happy to have another student, and he is a very talented student. He is going to present his work in the Netherlands next month, I guess. What kind of the research are you presenting? Your presentation title or something like that.
My presentation title is
Yeah, you can do. Yeah, some image stuff, right? Should be computer vision or no? Yeah. Anyway, yeah, you should. I think you need to prepare for the presentation. Yeah, in the conference. So the last one is Takuma. So can you say something?
Hello, I'm Takuma Ota at data science. I'm working for data scientist at the edtech company in Japan. I'm analyzing educational time series data or developing table data predicting model. That's it.
So you are kind of like helping a student learning process or something.
Yeah.
Yeah, sounds very nice topic, because this day due to the COVID, there is no the physical lectures, so that kind of things should be very important. That's it from our side.
Nice to meet you all.
Yeah, nice to meet you. Oh, comment. Oh, seems like there should be better way to share the screen. But yeah, as long as it works, yeah, I'm fine with it. Oh, let me try other way to share. Try to show. No, yeah. Then I think we can move on to our solution presentation, right? If anyone doesn't have any questions. Yeah, thank you. So, okay, yeah, I'm not so familiar with the Google Meet, so I'm a little bit messed up. Yeah, anyway, yeah. So, yeah, I'll get started. Yeah, first of all, thank you for hosting such a nice competition, so that we enjoyed a lot. So, yeah, I want to give the special thanks to the Foursquare team and the Kaggle team. Yeah, I think personally it's very excited competition, because I haven't seen such kind of task setting in the previous competition. So you know, the number of the record are very huge. Yeah, I'm not sure this is huge for you, but for us it's a huge. Yeah, it's literally the big data for us. So that if we consider the pair of this 1 million data set, it's very huge. So that in our solution, we need to think more about the throughput or efficiency, but we need to keep a balance between efficiency and the effectiveness or accuracy. So such kind of keeping such balance was very interesting for us. So yeah, then I think that this, the Foursquare service is very famous even for the Japanese people, so that we can easily imagine how this kind of solution used in this your service. I'm not sure whether this is actually, yeah, but yeah, Anastasia said something about that, so that we are able to imagine what kind of the motivation of this task. Yeah, thanks a lot, and thank you, Addison, as well. So that this is the agenda. So that we plan to give some self-introduction this part, but we already did that. So that I will directly jump into the solution overview and the solution detail and the discussion and the Q&A. Should be normal, the winners call one. I think you guys already have several winners call before, but I think most of the team also did such kind of also discuss such kind of things. Yeah, this is us. And the solution overview, I think except for third place, this approach is very common in all winning teams. So there's a two stage. The first stage, we want to somehow filtering less promising pairs, but we need to somehow get the high quality pairs with low computational cost. So that now I say that the promising but still cross gradient candidate pairs, and we utilize transformers. Yeah, I think transformer is utilized in many different areas recently, in addition to the NLP task. So that I think the one biggest finding from our side is transformer is very useful to find a good candidate in the efficient way. So yeah, unfortunately, so that we have some unfortunate leak there. So that I'm not sure how much we can generalize this idea, but I think this kind of approach should have some generalizability for the task. And so that this is one of the biggest the findings in the solution. And the second stage is this is good. The transformer is good, but still cross gradient, because we more focus on the efficiency rather than the accuracy. Yeah, if we focus on the accuracy on this side, it will increase the computational overhead a lot. So that's why we separate another stage, and then we kind of like train a bunch of the model and kind of like combine them. And the advantage of this approach is that we can split the task. So each people can train each model, and we can the mix up together, and eventually it works. We also try put more features in the transformer side, but eventually we find that this kind of the bunch of the model approach works. But I'm not sure because yeah. So because we are using somehow we implicitly use some leak. So the leak means the training data included in the test data. So the overfitting cause the result in the higher score. So I'm not sure the generalizability of the disparate. That should be fine. Yeah, we can discuss it later for each step. So yeah, this is the overview. So if you have any question, we can answer at this point.
Oh, very quick question there.
Yeah.
Based also on Tom's comment. So the transformer part here is not for filtering out candidates. It's just the ones that have already generated in the previous.
Oh yeah. So yeah, okay. Tom comment is right. So I think we first filter out the step there. So yeah, I'm sorry. Yeah, this part is mainly from Tom. So I a little bit misunderstand. Yeah. About that. So yeah, I think the first we somehow filter out based on the name similarity and the distance. Then we refine with the transformer. So in this case, our solution is more like the third three-stage solution. The first we roughly filter out the pairs with the distance and the name similarity. Then there's the two refining stage with transformer and a bunch of the models.
Great, thanks.
Yeah, thank you for that. Yeah, and thank you for Tom, so that I missed that part. Yeah, actually, we can also use the first stage pair in the later stage, but it results in the very high overhead. So the transformer was able to handle such kind of large number of the pair in an efficient way. Okay, then this is the part. Thank you, Tom. Yeah, the pair filter, not the filter. Yeah. I think we understand the point. So the first we utilize some transformer. I'm not sure everyone knows how it works, so that I just rough understanding of how we use the transformer in this competition. So in the normal usage of transformer for the NLP area is we just put such sentence in each cell, and we can consider until n length sentence. So this is a pen or above or something like that. So that then we can somehow not the currently I'm sorry, this is not a sentence level, so that it's a word level prediction. So like Bob is neutral or positive or something, so that we can predict some value for each cells. So we utilize this design so that we put the source, so that we want to check the pair. So that let's say I call the left side is the source and right side is the target. So that we put the source target here and put the target point in the right and until n. But the question is how to find the n candidate for each source. So that this is in the next slide. So the unique characteristic of this competition is somehow the distance is very accurate. So I think this is calculated by GPS in the cell phone. So that it's a very reliable source. So in another such the pair finding task, there is no much reliable source. For example, if we want to see the similarity of the image, it's hard to tell. But the distance is a very good metric, and this is a unique characteristic of this competition. So that there is a very reliable source there. But the distance is not perfect because sometimes GPS is not so accurate, and if it's in the same building, it's hard to distinguish. So that we also use the name similarities, but we found that the name similarity is kind of like country dependent. Some country the name similarity is very reliable, but some country is not. So that we optimize how many ratio to use for the distance similarity or the name similarity. For example, this is not the actual value. This is just the image. So that, for example, some country, the distance, we pick the 60% of the candidate from the most the closest the pairs to the source to the target, and the rest of the 40 is the based on the name similarity. Then this ratio is varied in each country, and there should be some around 200 countries in the dataset.
So you optimize this ratio for all the different countries?
Yeah. Then I think Tom, you can explain how we optimize it. We somehow say that if we know the perfect threshold, we check how the upper bound of the IOU, then so that we somehow check the recall value, so that how much we can cover the true positive in this list, and we see how much we ignore some the true positives. Tom, you can say something about that. Maybe this is your part, right?
Thank you. That's right. That's right. You said.
Yeah. So that we didn't calculate some very detailed score. We more focus on how much we can cover and how much we ignore at this point, and we somehow minimize the ignoring pairs. Try to minimize, but the large number of n increase the computation time a lot, so that we somehow see when it will be saturated. So that this is kind of like the saturated. So this is kind of like when I depict it. So that if we only use the geometry distance, so that this is almost a recall. So that almost 95% true positives are covered by this distance. But if we only use a distance, 5% for true positives are still ignored. Then we use some, we use the name, the store name, a point name similarities. Then it can reduce almost 2.5%. But we just use the same ratio for each country, like a 50-50.
Mm-hmm.
Then after that, we optimize the ratio for each country. Then we finally found that if with 128 source point with optimized ratio for each country, that we somehow say that only 1.1% true positive are ignored, and we somehow satisfy that.
So, yeah, that's clear. Thanks for that. I have one more question on the previous slide on the TF-IDF scores. I guess these were calculated for each country separately, right?
I think we did that. Oh, do you remember, Tom? I thought that we did it at the same time. TF-IDF is separated or
not
united?
Separated. Yes, united.
Yeah, I think the IDF values is kind of like work well with more document, right? So that's why we didn't separate it.
Oh, so you calculated the corpus was the entire.
Yeah.
In this case.
Yeah. And I didn't put the so that we use 2 and 3 gram. So that we didn't use the space split word, because Japanese, there's no split in the sentence. There's no space in the sentence, so that we use 2 gram and 3 gram.
All right. So that's my next question. How did you separate tokens for different languages?
Yeah. 2 and 3. So I think, yeah, we just use the scikit-learn function. It should be very easy. So, so the Tom, could you prepare some? So we can show some small small code base, right? So it's just a one-liner, right? So we just use the scikit-learn function.
Did you do any processing on the strings, or did you?
No, we simply use the scikit-learn function. So that Tom, could you prepare the code? I think it should be easy to find, right?
Okay.
Yeah, okay. So that I will show that it's very simple function, and we just utilize the scikit-learn function. So that we actually I also tried some pre-processing on the text, but yeah, but it didn't work a lot. But we at least use Tom, we also applied Unicode regularization, right? So that we change the Unicode, kind of like a regularized Unicode. So
yes, at first Unicode.
Yeah, for example, the Germany language has some the Austrian 2 dot on some alphabet, right? Yeah. So I think that we kind of like remove it with it also some. Yeah, we just use the code shared in the discussion. Then we somehow regularize the Unicode. Then we just use the scikit-learn function. So yeah, I think that Tom is preparing so that we can show that later. Yeah, I think that it's very easy to understand if we see the code. But we don't have a very special stuff for the similarity calculation. But TF-IDF is a very large matrix, so that how to handle is a little bit difficult. Not difficult, but we need to utilize the sparse matrix calculation method. So that like a CSR matrix or CCR matrix or something. But the TF-IDF calculation itself is very simple, and we rely on scikit-learn.
I added comment.
Oh, you put in something?
Low code.
Low code? Where did you?
Yeah, Google Meet comment.
Oh, so.
Oh, you use the TF-IDF factorizer directly with the row entries. Okay.
Yeah.
Cool.
Yeah. I optimized some what kind of n-gram works. Then I somehow diagonal it. Then I found that 2 gram and 3 gram works. Yeah, because we also try some pre-processing method, but it takes a lot, so we are not able to fit in the computational time, so that we just use a similar one. And this is kind of like the first stage. So I think if we use a more sophisticated method, I think we may be able to reduce this number. Of course, if this number is infinite, we can cover all pairs, right? But the infinite is not computable, then we just check. If we use a more sophisticated similarity, we may reduce this number, and it will be the more efficient. Yeah, this is for the first stage. So any other questions? Okay, yeah, we can come back anytime if you have a question. So this is the overview of the transformer, so that it's a little bit technical, so that I didn't go dive into the detail part, so that it's still coarse-grained the prediction, but we still put some the features like distance, or so that we have the TF-IDF matrix that we did some the singular value decomposition and put some value of it, or country or category, or something like that. Yeah. Then finally we predict the confidence value for each cell and see whether how much pairs we will pass to the second stage. And this is so that we use a very kind of a conservative decision. So that if the confidence value is more than 0.005, we pass the pairs to the second stage. Yeah, but why we apply this approach is we want to keep a balance between the effectiveness and the efficiency. Yeah, this is the first stage.
Can you go a little bit on the previous slide? On the bottom left corner, I'm trying to understand how you set up the feature space there. You have absolute features, which is you concatenated the features from the two places in a pair, and then you have the relative features, and you concatenated all of those together as the input to the
transformer. Yeah, this is the kind of yeah. I think this is also our design. So that now, so that we know that the source pair, and if in the same row, this is kind of like this is we already represent a pair, so that we put the both absolute and relative pair, so that so that each cell can have a kind of like a vector feature. So that for text case, the vector feature is just the embedding of the sentence, the word. But in our case, we handcraft this feature. For example, the distance to the P1 to P3 or P1 to P4. That for each cell we have some. I think so that each cell have let's say this to P1. In this case, it's a distance P1 P1. So that it's the or name similarity is also P1 P1 or some absolute features. Tom, do you know some good absolute feature to mention? Oh, yeah. Latitude and longitude on the country, or yeah. Does it answer your questions?
Yeah. So you put both the similarities and distance features, but also the raw.
Yeah.
Or absolute or embeddings of absolute features as well. Okay.
Yeah. But we only use a very kind of like a naive or very important feature because we didn't want to make this part so heavy.
And what is the XLM Roberta base name there? Is it an embedding or is it something else? Is it an embedding?
Or so this is the kind of like another BART model. So that this is just a pre-trained model. We don't train this model, but we can somehow input the name and we can get the embedding of this name, right? The embedding is a vector. Yeah, we just put that.
Thanks.
Yeah. Tom, do you remember how did the BART part contribute to this score? I think it's not so many, right? Very slight.
And not so large.
Yeah. I think the 1 point or 2 point in the leaderboard in the last digit, right? I guess. Yeah.
Yes.
I think I like this design with the transformer. This is kind of like a generalizable and flexible. We can put any feature there, and the computation of the transformer is very efficient, as recently large language model can work with huge data set. The score itself is not that bad, actually, but it's not enough to win this competition. So we need to work more on the second stage.
Sounds good. I'm not sure if you have a separate slide for that, but if not, can you talk a little more about the BCE loss function that you used and why IOU did not work?
Oh, the Tom could just elaborate something. Hello.
Oh, sorry. Yeah, BCE loss is better, so I don't know why IOU loss not work.
Yeah. I also remember that we discussed a bit, right? So one thing we discussed is so you know that the BCE loss is per cell loss, right? So that if this is a P1 and P3 is a pair, so that this is one. P1 and P4 is 0, so that it's a P1 and P4 is not a pair, so that we will this is 0, and we somehow calculate the cross entropy loss for each cell. But IOU is kind of like a low level measurement metric, right? I think. So that for each, so that in current metric, we calculate the IOU for each P1, right? Not so the low level loss function, I dare say. But the BC loss is a cell level loss function. So I think cell level loss function can learn more from the each cell feature. But if it's low level, we don't know which part contribute to this loss value. This is just an intuition, but this is what we thought during the competition.
Mm-hmm. So IOU did not converge during training. That's
I think the IOU loss was not so bad, but it empirically we just find that the BC loss is better in terms of the score.
Mm-hmm. Sounds good. Thanks.
Yeah. Actually, this is very common things in the deep neural network stuff. So we don't know why it's so good, why it's not so bad. Yeah, but I also have similar experience in other competitions. Binary cross entropy. So that each competition has their own metrics, right? Unique metrics. Then I try to design directly optimized for their metric, but BCE or in the tabular competition we can use just a log loss somehow outperform such self-designed loss functions.
Mm-hmm.
Yeah, I don't know why, but this is what we observed. Yeah, then I think this is the first part. Yeah, we have done with the first part. The second part is a very kind of like a simple, because another unique characteristic of this competition is it's relatively the feature is not so rich. So for example, name is very short and we don't have a description or the site, and the column is on there's I think that around 10 features, so that we were not able to do very detailed stuff in second place, but yeah, I'll go through it. The first of all, so that now we have we filter out some pair with this threshold, then we know the kind of like candidate pairs. I think there's in the training that they should be the 3 million or something at this point. 3 million is computable with GBDT. 3 million or 10 million. Or some remember how many pairs remains after the first stage? I think should around 10 million. Hello. Yeah, it's a bit long time.
I don't remember.
Yeah, should be 10 million, 10 million. Yeah, but still, what less than that?
Per ID is 4.1. So
no, I'm talking about the pair. Yeah, I think it shouldn't be. Yeah, I think that if it's in the order around a million, so that we can somehow compute the GBDT if we have a very huge memories. Then, so that we somehow predict for each pair. So the target is this is a pair or not, and we put some distance text similarities and geometry similarities or label encoding side, like just we change the ABC to 0, 1, 2, and we have the first stage prediction score from transformer. Then we put that. This so the how to say, this advantage of this approach is we cannot aware the information of the neighbor. So in the transformer, we can see what kind of the point kind of like a neighbor for this source, and the transformer somehow can aware which point cross each other in terms of the text similarity or distance similarities. Then, so that we can, so such kind of the neighborhood information can be considered. But in the GBDT, we split the data for each row and each pairs, so that they cannot aware such information. But if we put such kind of the prediction information, it could be implicitly considered. Then, yeah, this is the overview. Then this is the list of the features. So, so Tom, do you remember the name of the library of the text similarity?
Text similarity
library. Yeah, we found that there is a very nice library to calculate the text similarity, and it's very efficient.
Not rapid fast.
Oh, rapid fast, yeah. Rapid fast. Yeah. I think many team also use that. This one very. It was very nice. So that this computational limit was very tight. So we kind of like based on their benchmark. Yeah, it's very efficient. This library helped a lot us, and it can cover a lot of text similarities like Geshe or Levenstein or Jaro. Actually, we don't know how to calculate the text similarity, some of them, but this library implement a lot of such text distance, so that we just put it as a feature. And for name and categories, we also calculate the jack card or dice. This is kind of like a word level similarities. And the cosine similarity, so that we have TF-ID matrix. We already calculate that, so we want to utilize that. So then we put the probability of the transformer. Yeah, then we train the gradient boosting tree. So next, but GBDT is very nice for dealing with the kind of like a tabular data or number data. But in this competition, the name has very rich and important information, so that we also utilize the BERT or transformer, pre-trained transformers, which is very nice in this, which shows a very nice performance in many domains. So, so that we use the Muluk or the XM robot base. We try many pre-trained models in the Hugging Face homepage, so that there are a lot of models in the Hugging Face that we try one by one, and we find that MLOOK and the XM Roberta base and large what's good. The input is a text as shown in previous slide, like this. Then this is the text we input. S is a kind of like a special character to let the model know where is the split of the sentence. the sentence split kind of like a marker. Then we put the country name, category, and we concatenate all text features in one text. Then and we also put the probability of the transformer in the first stage and the Haberstein distance of the name, just in case. Then we put the into the transformer. Then finally we calculate the. Oh, I'm sorry. So the text part is went through the transformer. Then after that we have some vector, and we concatenate this vector and the numerical features. Then finally we just apply logistic regression. So this is part from the I think Kohei, or they want to say something about in this part. Yeah, I think that they are shy. Yeah, I can totally understand. Yeah, I'm a fourth year PhD student in this September, but when I come here 4 years ago, I wasn't able to speak English at all. So yeah, I can totally imagine there. But the key idea, I didn't invent the key idea. So the key idea is from the Tom designed this first stage, and the second stage is designed by Kohei and the teammate. I also contribute some each part, but the large key idea comes from the other teammate. Yeah, and I found that this team was very nice, so that we somehow utilize each the expertise. Yeah, that's it for our solution. So we have some few discussion points, but if you have a question, we can answer it at that time. At this time. Yeah, sounds good. Hope my explanation is clear enough. I hope so. So this is a discussion. So if it's possible to share, I'm not sure whether this is confidential information or not. But can you ask how the Foursquare distinguish whether a point is a new point or already in the DB?
In the database that we already have?
Yeah. So how can we distinguish whether this is a new point or someone check in so that this is already, so that somehow how to get the pair in for the new entry?
Yeah, pretty much we are following a similar process as this one. So we check for candidates that are close to the new place that we want to add in the database. If we have some candidates that we feel they are the same place in reality, then we add it to an existing, let's say cluster or place of interest that already exists. If they are distinct enough and it seems to be a new place, then we create a new place of interest based on this new entry, and we add it in the database.
Oh, is that done by batch processing, or it's kind of like is that decided in online or to create a new point?
That's an interesting question. It's a little bit of both, depending on the source information. If we get information from sources that send us bulk numbers of data, we do it in bulk processing. If there are information coming from users, individual users that may create a new place, then the process is a little different and goes on one by one.
I see. Yeah, that makes sense. Yeah, because our approach is somehow batch processing, right? So like a daily or something. So but we cannot handle such kind of online stuff. Yeah, that's why I'm a bit curious about that.
That's a great question. Based following up a little bit on that, what are the training times for the models that you have?
Oh, that's a good question. But I think the transformer is relatively efficient, right? Oh, Tom, could you say something about the computation time for training?
using 32-core CPU machine and not strong GPU, around 8 hours or 12 hours.
Yeah, 8 hours is not, but you use 800, right? Is that correct? 800.
800?
The NVIDIA 800. Is that correct?
Yeah, not 800.
Oh, which?
Not strong GPU.
Oh, so can you say specific one? I thought that you use 800. As I said, they can use the company resource. So yeah.
I'm not sure.
No worries. Just to get a general sense of how complicated the training process is. That sounds good.
Yeah.
Maybe Yuki knows the details of machine.
He used NVIDIA T4 4 NVIDIA T4 GPUs.
Oh, T4 is not so decent, right? Yeah, that's good. Yeah. Oh, I remember that the CPU has more overhead, right, at that time.
Yes.
Yes. But need more CPU for us. So
yeah.
I used 32-core CPU.
Yeah. I remind that. Yeah. So that that there are a lot of text information, so that it levels the specific implementation topic. So that in each iteration, we somehow recalculate these distances, like a text distance or something. Like, actually, this is a very high overhead. Some text similarity needs much time. And in a PyTorch dataset, we calculate this distance in each time, because at first we tried to store it somewhere, but it was very huge. And if we store it in the hard disk, it's there's a large overhead. But we cannot store it in the memory. So, but this part is done by CPU. So the GPU was not the overhead in the transformer part.
That's nice.
Yeah.
Thanks.
Yeah. For other part, so GBDT takes 12, not 12, 3 or 4 hours. Yeah, actually, it depends on the transformer threshold, so that I didn't remember, but it's not high. Go ahead. Do you say something about this part?
It's 2 hours per epoch, and I trained 5 epochs, so 10 hours with NVIDIA V100.
Oh, I see.
Gotcha.
Yeah, but this is for one CV, right? CV split. Oh, I remember we trained 5 models for each, right? Is that only for transformers?
Yes.
Oh, yeah.
But all data training.
Oh, so in this part is we didn't split the CV, but for transformer we need to somehow measure the performance, so that we train 5 models in the first stage. So yeah, but this is for production we don't need to train 5 models, but this is a competition, we need to track the performance, so we train 5 models.
Sounds good. Thanks for that.
Yeah.
I think we have 2 more minutes. So
if sorry. Yeah.
One question for us. That'd be great.
Do you have any other questions from our side? I think these points are what we came up with before this meeting. I think the third place owner use deep metric learning. So, and this is more question for Addison. So fortunately, we were not able to know where we are in the recalculated leaderboard, so that we cannot judge whether this approach is generalizable or not. So we hope to know that. Yeah, that's it.
Well, thank you. My short answer, because we are limited to time, is I believe that your model actually errored out when we ran it against the new data set, but we do not look into individualized code or errors at Kaggle unless we're trying to troubleshoot. So I think that's actually, so I actually don't think we were able to get you a new leaderboard score, hence some of the, because it did not generalize to the new data set, which was different size. Anyways, we wanted to thank you so much for your time. Obviously, this has been great work. The second place is a fantastic finish. Although I know that you've had a number of second place finishes over a few competitions recently, so you're holding out for a first place coming up soon.
Yeah.
We have a few more of these calls coming up over the next few days, at which point we will then issue the prize payment. Once again, congratulations. Thank you so much for your great work and presentation.
Yeah.
We look forward to hearing more.
Yeah, this also by chance, can we know some which place we are in? So that you only disclose the top 5 teams, right? So that unfortunately we are not there. So that we just roughly know where we are in the new rank.
Yeah, so I'm pretty sure, I'm not 100% sure, but I'm pretty sure your code did not successfully run on the new data set. It errored.
Oh, it caused some errors. Oh, I got the point. Yeah, that makes sense. Yeah.
Yeah, but sorry, and then just for the marketing side, I'm really excited for you, and congrats on the second place. Would you be interested in doing a blog post with us, just like as a feature, and like to present your data, and be working with Foursquare down the line?
Oh, yes. So, I'm sorry, I didn't get what this.
Oh no, sorry. So we'd just like to, from the marketing side, we'd like to have you highlighted or featured in a blog post or a webinar, if that's okay. You can present your work.
I'm making another room.
Competition. So I know this is we're like on the last very minute. So I would just like to ask you, if not, it's also okay.
Oh yeah, that would be great. Yeah, thank you so much. So we can present.
Okay, great. So I'll be on contact after this call.
Yeah. Oh, I'm sorry. I'm sorry. I misunderstood that. I thought that you said that we can present this work somewhere, but somehow asking we can present in your company or somewhere, or.
Yeah. I'll contact you furthermore after.
Yeah. I think that it should be efficient. It's already in the last minute. We are getting over the time. Yeah.
Thank you.
Yeah. See you.
Thanks
so much.
Congratulations again.
Congratulations.
Thanks for a good competition.